Let's start with the violent birth of a black hole. When a massive star exhausts its nuclear fuel, its core collapses inward, crushing matter into a singularity and severely warping the surrounding fabric of spacetime. These remnants are the most extreme, gravitationally intense objects we know of. Ever since Albert Einstein developed the theory of general relativity in 1915, we've understood that black holes possess an event horizon, a boundary so dense that not even light can escape its pull. But while we understand how they trap matter, we have lacked a way to predict their long-term survival. Based on observations, a black hole faces two highly divergent paths. It might persist, accumulating enough matter to become a supermassive monster, anchoring the center of an entire galaxy. Or it might slowly bleed out its energy and evaporate into nothingness. To determine which path a black hole will take, we can turn to the Black Hole Structure Stability Theory, or BHSST, presented in Nathaniel Faxon Cherier's book, My Dear Universe. This framework provides the exact equations necessary to calculate a black hole's lifespan. By weighing specific variables against each other, BHSST allows us to view black holes not as unpredictable cosmic anomalies, but as quantifiable entities with a mathematically predictable destiny. Determining a black hole's stability ultimately comes down to a mathematical tug-of-war. On one side, we have the physical forces that feed it and promote its growth. The first of these growth metrics is the black hole magnetic field strength. This measures the intensity of the magnetic field surrounding the event horizon, a crucial factor that dictates stability by influencing how spacetime curves around the singularity. The second growth metric is the black hole accretion rate evolution. This tracks how efficiently the black hole gathers surrounding gas, dust, and starlight over time, dictating how fast it builds its mass. This chart shows the accretion rate compared to a black hole's total mass. The rate at which material is gathered scales exponentially. A stellar mass black hole might consume a tiny fraction of a solar mass per year, while a supermassive black hole exceeding 1 million solar masses can devour up to 10 solar masses in that same timeframe. When a black hole combines highly efficient accretion with a dominant magnetic field, these two physical engines drive the object toward infinite persistence. On the other side of this tug-of-war are the forces of decay, operating on a microscopic quantum level at the edge of the event horizon. Here, we calculate the black hole evaporation time. According to quantum mechanics, black holes emit a slow leak of thermal energy known as Hawking radiation. This process establishes the timeline over which a black hole will slowly lose mass and shrink. The final metric is black hole entropy, which measures the internal disorder and randomness trapped within the black hole. Higher entropy heavily influences instability, accelerating the timeline of decay. If the massive forces of magnetic growth and physical accretion falter, these microscopic quantum decay mechanisms will win the tug-of-war, inevitably erasing the black hole from existence. This graphic shows the Black Hole Stability Criterion, or BHSC. This core equation weighs squared growth forces, magnetic field and accretion, against decay forces. The math yields a clear threshold. Below 1, it is stable indefinitely. 1 or higher, it rapidly evaporates. This score is not permanently fixed. Dynamic cosmic events, particularly violent binary collisions between two massive bodies, can drastically alter a black hole's mass and rotational spin, recalculating its stability score in real time. This chart visualizes collision outcomes. Merging neutron stars forming a black hole have a 90% probability of stability. However, high rotational spin changes the math. A spin parameter exceeding 0.8 enters a danger zone, guaranteeing an unstable result. After any violent celestial merger, the BHSC score acts as the definitive mathematical judge of that black hole's cosmic survival. Stepping back to the macro scale, those stable, low-scoring black holes physically shape the universe. They persist long enough to become the supermassive engines powering active galactic nuclei, definitively regulating star formation across entire galaxies. Astrophysicists verify the physical reality of the collisions that create these stable black holes, using ground-based detectors like the LIGO Observatory in Washington state. LIGO works in tandem with international counterparts like the Virgo interferometer in Italy to detect invisible ripples in spacetime caused by massive black hole mergers. Once a gravitational wave is detected, Optical instruments like the Hubble Space Telescope are repositioned to hunt for visible electromagnetic aftermaths, such as kilonova debris. Following optical observations, massive radio telescope networks, like the Square Kilometre Array Precursor, trace the long-term energy signatures emitted by these newborn, stable black holes. Through these coordinated observations, the abstract theoretical math of BHSST is continually validated by the physical architecture of the cosmos and our global network of observatories. The greatest achievement of BHSST is its ability to bridge two distinct areas of physics, the massive gravitational scales of general relativity and the microscopic thermal decay of quantum mechanics, bringing them into one cohesive mathematical framework. This newly unified scientific approach provides the essential mathematical groundwork needed to finally resolve the long-standing black hole information paradox. By quantifying the exact forces of growth and decay, we elevate black holes from unknowable voids to precisely charted entities. To continue exploring the deepest mysteries of the cosmos, hit the like button and subscribe today.